Hey everybody, it's Miss Davis. We are going to today talk about nuclear transformations. This is chapter 25.2 in your textbook. So let's go ahead and get started. Bellwork question for today. Put in order from the most penetrating to the least the three types of radiation, and then why are some particles more powerful than others? So pause the video, try it, write it out, and then when you are finished, come back to the video, unpause it, and we will discuss it. So hopefully you had a chance to put this in order. Most penetrating, you should have gamma rays, okay, then beta, then alpha. And the reason that some of them are more powerful than others, gamma rays are going to be so small and so fast that they can go through almost anything. You have to have something strong like lead or several feet of concrete in order to create a barrier. Beta particles, not as strong, not as small, they're kind of medium, so they can get stopped by something like aluminum, but anything softer than that they can go through. And then alpha particles, those are stopped by your skin, your clothes, just because they're the biggest and the slowest. So your essential question for today is, how do atoms undergo changes to become new atoms? Okay, so we're going to talk about basically how is it that we take this type of atom and then turn it into something completely different by using either decay, or we'll talk about transmutations later. All right, so first thing here, nuclear stability and decay. If you recall from when we started learning about the nucleus and the subatomic particles, our protons, neutrons, and electrons, the neutrons and the protons, they're both in the nucleus, which is kind of weird because that means the nucleus has all positive stuff in it. And so really the neutrons are in the nucleus also. They kind of create a buffer in between the different protons. And then this force that holds everything together is called nuclear force. So even though the nucleus is all positive, and then so the protons are all positive and the neutrons are neutral, they have no charge, they're acting as a buffer, and that nuclear force will keep everything together. Okay, so, and then really the stability of an atom or of an element will depend on the ratio of neutrons to protons. So the bigger the neutron to proton ratio, so if there's more neutrons than there are protons basically, that's going to determine if the element is stable or not, and how stable it really is. So, and then also depending on the type of, or the ratio of neutrons to protons, that's going to determine the type of decay that occurs. And there's actually 4 types of decay that we're going to talk about here. Okay, so the first type of decay is called beta particles, or beta decay. And this is when you have too many, okay, okay. This is when you have too many neutrons. Oh. Sorry, got a fussy baby today. Here. You have too many neutrons and not enough protons, you will have beta decay. So basically what will happen is the neutron will spit out this beta particle. So it's kind of like an electron. It has that negative charge. So if you have something that is 0, like a neutron, and it gets rid of something negative, it's actually going to turn into a proton. Okay, so basically what that looks like, so this right here is our beta particle. Okay, so notice that it has a mass of 0 and it has a charge of -1. Okay, that's kind of where it's like an electron. And so if carbon goes through, or excuse me, if nitrogen goes through beta decay, it will create carbon with a mass of 14. So it'll create what's called carbon-14. Okay, and we'll actually talk about that more a little bit later. Come here, Chunk. Okay, so nitrogen with its atomic mass of 7 will go through beta decay. So nitrogen plus that beta will give you carbon-14. It's carbon because it's got six protons, but it's carbon-14 because its mass is 14. Second type of decay is what's called electron capture. So this is kind of opposite of alpha, of beta decay. This is when you have not enough neutrons and you have too many protons. So what's going to happen is the nucleus will capture an electron, and so it takes one of those protons, because if you have something that's a +1 charge, and you, whoops, what did I do there? And you add something that's a -1 charge, well, if you have +1 plus -1 or +1 minus 1, you're going to get 0, which is your neutron. So this is how you create new neutrons, and create with air quotes because we're not really creating anything, we're just adding stuff to change it around. So if you have carbon 11, okay, so that means it has 6 protons and it's got a mass number of 11, okay, and you add this electron, you now have boron with, and so you have, now you have boron, because boron, it's 5 protons, okay, but because you added this neutron, you now have 6 neutrons, so your mass is still 11. Okay, so without adding that neutron, your mass number would change also. So electron capture. Okay, and you don't really have to worry about this little neutrino thing. Bless you. Bless you. Okay. Third type of decay is what's called positron emission. And so what a positron is it's a subatomic particle. It's a piece of what makes up protons. So the proton will change into a neutron by losing that positron. So instead of adding an electron like we do in the electron capture, we're going to get rid of one of these little positive particles. So if you have something like carbon 11 again, okay, it goes through proton emission to become boron 11 because it's getting rid of that positive. So it's not adding neutron, or it changes into neutrons by getting rid of that little positive charge. And then finally, your last type of decay is alpha emission. We've already talked about this, okay? This is when you have an alpha particle and you get rid of it. So your mass number will decrease by 4, your atomic number decreases by 2. It occurs in your radioactive elements. So anything with an atomic number greater than 83 is technically a radioactive element. Okay. So here's an example here, uranium. Its element number 92 has a mass of 238. It goes through something. It goes through your decay event. It goes through some sort of happening that makes it want to lose this alpha particle. So then up here, here's our alpha particle. It looks like helium. And then down below, we've got thallium-234, which gave it a proton number of 90. So we lost 2 protons, and then we lost 4 neutrons. Okay. All right, next thing we're going to talk about is half-life. This is basically how quickly, you just spit up all over me. Thank you. This is how quickly the radioisotope will change into something else, basically naturally. So everything will go through a half-life in some way, shape, or form. Some atoms and elements it'll be a few seconds. So it'll change very, very quickly. Others are very, very stable, and it takes billions of years for them to go through a half-life. The half-lives can be used in radioactive medicine. So this is something like if you go to get like a CT scan, or they're doing work on your like heart, they will inject you with a radioactive substance, and that will create the ability to see that on the CT scan better. And then you also have the dating of ancient objects. That's called radiocarbon or carbon dating. And basically what they do is they look at the amount of carbon-14 found in that substance, so they can carbon date like fossils and like ancient tools using this method. All right, so I'm going to pause the video here just because this next part will take longer than 5 minutes, and that's all I have left on my recording. So I'm going to pause here, and then you can play the next video to determine how we calculate half-life.